Good day, cadets. In this final video, we are going to explore the calculations in the electrolysis process by looking at Faraday's constant and Faraday's law. Yes, it's that same Faraday fellow you have heard of in physics. He obviously had nothing better to do. When an electrolytic cell is switched on, the electrical energy provided by the power supply depends on the current used and the duration of the process. To express the electrical charge supplied during electrolysis, we use the unit coulomb. 1 coulomb is simply the quantity of electric charge supplied by a current of 1 ampere in 1 second. The formula shown can be used to calculate the amount of electrical charge supplied during electrolysis given the current and duration. Now, the letter Q is generally used to represent electrical charge. However, to avoid confusion with the reaction quotient or Q that we have learned earlier, we will use the letter C instead. The total electrical charge or C provided by the power supply during electrolysis can also be calculated by using the number of electrons that have passed through the cell. Thus, we have a second equation to calculate C, as shown. In the studies of chemistry, however, we typically express the amount of substances, including electrons, in moles. We can now introduce the Faraday's constant to help with calculation using moles. 1 Faraday is the amount of electrical charge carried by 1 mole of electrons. Generally, we just express 1 Faraday as equal to 96,500 coulomb per mole. We can now express the second equation in terms of the Faraday constant as shown. Take note that the number of moles of electrons, or Ne, here is the number of moles of electrons exchanged between the anode and cathode during electrolysis. And here are the two formulae that we can use to calculate the total charge, or C, delivered during an electrolysis process. To simplify things, we can just use this equation. IT equals to NF, where I is the current expressed in ampere, T is the duration of electrolysis expressed in seconds, and E is the moles of electrons transferred between the anode and cathode, and finally F is the Faraday's constant. The good news is, all calculation that we are going to attempt from this point onwards will only use this simple formula. We have just been introduced to the Faraday's constant. So, what is this Faraday's law? In electrolysis, we will obtain products at both the anode and cathode. It is therefore very useful for us to know the amount of products formed at each electrode. Usually, we are interested in the mass or volume of the products formed. The relationship between the amount of products formed, the current, and the duration of the electrolysis process is described in Faraday's law. Faraday's law simply states that the amount of products formed at the electrode of an electrolytic cell is directly proportional to the total electrical charge supplied during the electrolysis process. In other words, the higher the current used, the higher the amount of products that will be formed, and vice versa. Also, the longer the electrolysis process occurs, the higher the amount of products that will be formed, and vice versa. Let me lead you through an example. Please take a moment to read through the question. The current used is 1.5 ampere, and the electrolysis process took place for 6.23 hours. You are required to determine the volume of products formed at standard temperature and pressure, or STP. Now, let us start by writing down the half reactions at the anode and cathode. Since we are using dilute sulfuric acid as the electrolyte, the anion that will be discharged at the anode is the hydroxide ion. And the cation that will be discharged at the cathode is the hydrogen ion. We now know that the product at the anode will be oxygen gas, and the product at the cathode will be hydrogen gas. The overall equation can be written by combining the two half equations. Remember to ensure that both half reactions have the same number of electrons before adding them up. Next, from the IT equals to NF formula, we can see that we already have three of the terms given in the question, including Faraday's constant, which is always 96,500 coulomb per mole. Seems like we need to solve for the number of moles of electrons, or Ne. Let us solve it then to obtain Ne. Now, how is solving Ne help us to calculate the amount of products formed? Looking at the anode half reaction first, we can see that 1 mole of oxygen gas is produced when 4 moles of electrons are released in the oxidation process. The mole ratio of oxygen gas to electron is 1:4. Since we now know from the previous calculation that the number of moles of electrons transferred between the anode and cathode is 0.35 mole, we can now determine the number of moles of oxygen gas produced as shown. The number of moles of oxygen gas produced at the anode is 0.0875 mole. We repeat the same calculation at the cathode. From the half reaction, we can see that 1 mole of hydrogen gas is produced when 2 moles of electrons are received in the reduction process. The mole ratio of hydrogen gas to electron is 1:2. Therefore, the number of moles of hydrogen gas produced at the cathode is 0.175 mole. We can now calculate the volumes of oxygen and hydrogen gases produced at the electrodes at STP. Utilizing what you have learned about molar volumes in semester 1, we can now easily calculate the volumes of oxygen and hydrogen gases produced as shown. Notice that the volume of hydrogen gas produced is twice the volume of oxygen gas produced. And here is another example for us to look through. Please read through the question before we proceed. Are you ready? Now, at the end of the electroplating process, the car bumper must be covered with 0.01 millimeter of chromium metal to give it the West Coast Customs look. How long will this process take in hours? Let us start once again with IT equals to NF. Since we need to find the duration of the electroplating process, let's rearrange the formula with T as the subject. Since current is already given in the question, we are only missing an E to calculate the time taken. So, let us find an E first by using the half reaction given in the question. In this question, we can calculate the mass of chromium plating formed by using the thickness, surface area, and density information provided. To calculate the volume of the chromium plating, we multiply the area of the bumper with the thickness of the chromium plating. We can now calculate the mass of chromium produced by using its density. Using the atomic mass of chromium, the number of moles of chromium produced can be determined as shown. We can now use this information together with the half reaction equation to calculate the number of moles of electrons needed. From the half reaction, the mole ratio of chromium produced to the electrons received is 1 to 6. Since 0.346 moles of chromium have been produced, the number of moles of electrons received must be 6 times that value, which is 2.076 moles. We now have the final piece to the formula. Inserting all the values required, the duration of this electrolysis process is 2.23 hours. Note that this question specifically asks for the duration in hours. Otherwise, you could just leave the answer in seconds. And now, cadets, we have reached the final exercise. Please pause this video as you attempt the exercise. Once you are ready, press play to continue with our answer discussion. Ready? Let us look at the answer. For A, since a molten electrolyte is used, only one anion and one cation will be discharged at the anode and cathode respectively, as shown. For B, to obtain the overall equation, just add up the two half reactions above. Note that the number of electrons are already the same in both half reactions. For C, as can be seen in the half reactions above, chlorine gas is produced at the anode and molten magnesium is produced at the cathode. Why molten magnesium? This is due to the high temperature required to produce the molten electrolyte. So any metal produced which are normally solid at room temperature will melt at this high temperature. For D, use the formula C is equals to I times T. For E, use the formula C equals to NE times F. Since we already know the value of C in question D, we can easily calculate the number of moles of electron, or Ne. And finally, for F, use the mole ratios of product to Ne as seen in the half reactions at the cathode and anode to calculate the amounts of product formed. Since the STP information is given in the question, gaseous product amount must be expressed as its volume. It is now time for me to bid you farewell. Thank you for being part of our PPPU family. Insert tears of sweet sorrow here. And on behalf of the chemistry team, I wish you all the best for your final exam. Mun terkasar kata, ibuh terluka. Mun terlembut kata, ibuh tergoda. May the electromotive force be with you.